Okay. Well, let's go over this problem. And so the idea is, okay, now we have a friction force. What's our acceleration? Or at least let's understand the problem, draw a free body diagram. So if I were to let me draw the mass a little off to the side so to isolate it. So this is my mass. The normal force would go like this, exactly perpendicular to the plane.
So we're not using the same coordinate plane that you used on the
I am going to use the same coordinate system. So x is always along the plane, y is perpendicular to the plane. And as long as the plane itself is not accelerating, this is the most convenient way to do these problems.
Wouldn't n be pointing straight up since it's perpendicular to the plane?
No, it's perpendicular to the...
So like,
Yeah,
you're
it's
just
like
leaving
this.
the coordinate plane rotated then?
Yes.
Okay.
Yes.
You're not like...
Yes. I can't happily re-rotate this and
Okay.
resolve it. You could do that if you want, but I like to do it this way. And then the friction force is up like this. I'm just going to label it as friction. Okay. This angle is theta here, and this is the component of the gravity force in the x direction. That's mg sine of theta in magnitude. That's the length of this part of the vector. All right, so the sum of forces in the x direction, what are they?
mg sine of
mg.
15 minus
mg sine of theta
negative.
minus the friction force because that points in the negative x direction. And all of it does. Minus the magnitude of the friction force. And what's that equal to?
Mass times acceleration.
Mass times acceleration in the x direction. All right, so this thing is, so if I plug in numbers, what was this? mg sine of theta?
55. 80.
Yeah, it's
55?
Yeah, 500.
Yeah,
800.
80.
Yeah.
Like,
80 newtons.
minus
Minus
5,000.
5,000 newtons. Equal to m a sub x.
580.
So that would be 580 newtons
Mhm.
is equal to m a sub x
And then
divided by m. And so
Which is
what was m?
0.264.
21.
Oh, sorry.
And what was that number?
0.264. No, 64.
64.
64.
264.
64.
Okay. All right. That makes sense. What to do?
Yeah.
All right. A lot of times we don't know what the actual friction force is. You might just be given the coefficient of friction. Okay? In which case the friction force and the normal force are related. So let's go ahead and solve one of those ones. So now we have a friction force. Yeah, it's this one. Okay. So, I'll just draw this. I'm going to do this with a general angle. So again, I always find it easier to do it with general angle and then I can plug in numbers at the end. Let's do the following problem. Let's say that I have a block that is experiences a kinetic friction force, so it's sliding down a plane, and that there's a coefficient of kinetic friction UK. This isn't the friction force. This is the coefficient of friction, so I'd have to multiply this by the normal force. Let's go ahead and draw a free body diagram for this to see if we can figure out the acceleration down the plane. So I'm going to separate this out off to the side. I'm going to draw the normal force on it, like that. The weight force goes straight towards the Earth's ground. This angle is theta. And then what other force do I have on it?
Friction.
Friction, and if it's actually moving, well, we know that it's going to be in that direction. And what I want to do is just add up these forces, set the result equal to ma. And I know that if I introduce a tilted coordinate system like this, that only the x component of the acceleration will be non-zero. That is, it doesn't just jump off the plane or fall through it. So so that'll be, so we only have to really worry about the acceleration in the x direction. So we got to find what parts of the weight are in the x and y direction. So this was, what part was this in the x direction?
This one.
And the sine of theta. And what about the x direction, or the y direction, along the y
And
direction?
cosine of theta.
All right. Like that. And then this is magnitude of the weight is. Okay, let's go ahead and do this. So I'm going to sum up the forces in the x direction. So if I sum up the forces in the x direction, I get mg sine of theta, positive x direction, and friction force in the negative.
But that's also going to be mu normal force, right?
Yeah, that's equal to max. So in this problem, this is simple. We already knew the friction force. Here we don't know the friction force. But I do know that it's related to the normal force by the coefficient of kinetic friction. So this would be mg sine of theta minus mu k times the magnitude of the normal force is equal to max.
Times the magnitude.
Well, good, except for the fact we don't know what the magnitude of the normal force is, do we?
It would be equal to mg cosine theta.
Yeah, so now we have to do one more equation to prove that. You can see automatically that it's going to be that mg cosine of theta. But let's go ahead and apply Newton's second law and actually see that. So you have to do the y equation now. So sum of forces in the y direction will be the normal force at all points in the y direction. And then the mg cosine of theta points in the negative y direction. And that's mass times acceleration in the y direction. But this thing doesn't accelerate through the plane, so we're going to set this equal to 0. So, solving for the normal force, I add that mg cosine of theta to both sides of the equation. The normal force is mg cosine of theta. Good. Now what can I do?
Sub that in there.
Yeah, now that I know the normal force here, I just take this, put it into the that x equation. So this is this is an extra couple of steps from previously. so I get M, this becomes mg sine of that angle minus coefficient of kinetic friction times mg cosine of that angle is equal to MAX. Now if I want to get a sub x, what should I do?
Divide by the mass.
But, yep, divide both sides of this equation by the mass. That's the same thing as dividing every term by the mass. And I would see that I'd get g sine of theta minus mu k g cosine of theta is acceleration in the x direction. Or I can even write it like this. You don't have to, I mean it's all the same. So you want to do a quick example with numbers?
Sure.
This one will be a slight twist on what we just did. Slight twist. So, let's say I have a block on a plane. All right. And we find at theta equals 20 degrees. So this plane can be adjusted up and down, say. And at this 20 degrees, we find that this block moves, or slides, I shouldn't do have a sliding. At 20 degrees, we find this block slides at a constant velocity. Block slides with constant velocity. So the question is, what is mu sub k, the coefficient of kinetic friction? So let's go ahead and do this. I'm going to do it from scratch because I don't want to have to memorize any of these equations. Okay. It's like baking a cake from scratch. It's always better.
I don't know, that's a pretty good mental
Okay. Maybe a little more time consuming at times. All right. So let's go ahead and draw a free body diagram for this block. So what are the forces on it?
There's normal force in the y
Normal force, okay.
and then the weight force going straight down.
Weight force going straight toward down.
You said, is it friction? Yeah.
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 So we'll put the friction force going like this. Okay. And I'm going to introduce a tilted coordinate system, like you always do for these inclined plane problems, unless the whole plane is accelerating, but we won't do those. And so my incline, with that, I get a coordinate system like this. This is putting up the weight along the coordinate axes. I get that this is the angle theta there. Okay. And I get that this would be mg cosine of theta. This would be mg sine of theta. And we know that this weight force was mg. So if I want to sum up forces in the x direction, I can do exactly the same thing as I did before. It'd just be mg sine of theta minus
Minus the.
mu kn.
Mhm.
That's the friction force. That's equal to max. Now, if it's moving at a constant speed, what's its acceleration?
0.
0.
0. Good. Sum of forces in the y direction is, what are the sum of forces in the y direction?
Normal.
Normal force goes in the positive y direction.
And then
Friction is negative.
mg cosine of
Minus mg, is it cosine and is the friction in the y direction?
No, no,
mg
friction's the
cosine
gas.
of
Cosine
theta.
of theta.
mg cosine of theta. This was the friction, by the way, I skipped a step. Cosine of theta equals 0, because it's not accelerating through the plane. And so normal force is mg cosine of theta. Let's take this, plug it into here. And I would get mg sine of theta minus mu k mg cosine of theta. You see what I did? I just substituted what the normal force was back into here. Equals 0. So what should I do if I want to figure out what this is, the mu sub k?
Do you have to do quadratic?
You should subtract over,
Oh, yeah,
add over the
subtract
mu
over.
sub k.
Okay,
and
I
then
can do
divide
that.
by.
I'll do mg sine of theta is equal to mu k mg cosine of theta.
And then divide by mg cosine
Yeah.
theta.
Ooh, yeah, I could do that.
So mu is basically just sine theta over.
So it would just be mg tangent of theta.
Well, here, do these mg's, don't they cancel
Yeah.
out?
Yeah.
M, G cancel out.
Mhm.
This whole thing cancels. So I get uk is sine of theta over cosine theta. What was that?
3/6.
Okay. So, 20 degrees. Plug in. Plug in what that is. And what do you get?
0.364.
0.364. Huh, pretty good. And note, one thing that this illustrates too, this type of thing, there's a lot of cancellation of MGs. I never gave you the M, did I? So, but you were still, I was still able
But
to
the
figure
end
out
is
that
gone
problem.
anyways because the-
So it's, because everything, that M cancels out of everything.
So this doesn't have a unit, right? It's unit this?
Yes, that's right, it's just a number. Okay. I guess we'll do one more thing today. Did a lot of blocks on plane problems. There is one thing that I've been meaning to cover, and it just seems like every day it gets pushed to the end and I never get it. That is the actual law of attraction between masses. Now we said that if you're on the Earth, so this is the Earth, and you're on the surface of the Earth, the gravitational force you experience will be mg, where your little mass on the Earth. That's a very special case, and it's of an attraction between this mass and the Earth. Newton actually came up with the whole idea of universal physical laws. There wasn't such an idea really before Newton. I don't think, although, I mean, he definitely came up with the first expression for one. And what he realized is, wait a second. Let's say that let's imagine you're a little mass up here. Let's imagine you were shot out of a cannon really fast on top of the mountain. flying, okay? Now, he knew that if you fire out of the cannon, you come back down to the ground. Well, that's interesting. What happens if you kept on going a little faster? Well, you come back to the ground a little bit further off, right? Now the Earth, though, is a sphere and it's curving down. The ground's actually curving down, right? So he said, okay, what happens if you fire really fast? And this thing would curve down and it would keep curving because it would never hit the surface of the Earth. See, this path curved downwards towards the ground the entire time. But because the Earth is curving too, it never is able to hit the ground. He said, wait a second. That strikes me a whole lot like things orbiting the Earth, doesn't it? So he goes, wait. Maybe the gravity is actually something that is the same force that's holding us to the ground is actually responsible for keeping things in orbit around the Earth or around the sun. Wait, because he knew that there were things in orbit around the sun as well. And so then the idea becomes, wait, maybe there's this universal law of gravity that's doing all these things with all the planets and all the and the sun and all that, and it's all keeping all of those things orbiting. And he was aware of something called Kepler's laws, which were that planets orbit in an ellipse. They orbit. They know there's a relation between how long it takes to orbit and how far away from the planet it is, and all that stuff. And he knew those laws. Those were done experimentally by Kepler before Newton. But Newton decided, okay, what type of force, gravity force between two masses would create this orbit that would obey Kepler's laws? And what he came up with that seemed to fit all experiment was the following relation that let's call this the mass m, little m, that the force on that little mass would have a magnitude of some constant times the mass of the object it's rotating around. I'm going to call the mass of the Earth ME in this case, m, over the distance between the centers of these objects, so r. I'm going to call this r, squared. And it points direction of this force is attractive. Force is very attractive. It always points they always point directly towards the center of each other. So the force here would be downwards. When this mass gets over here, the force here would be over like that, pointing towards the Earth. When it gets over here, the force would be that way. That's what I mean by attractive. It always wants to be pulled towards the center of the Earth. And of course, there's Newton's third law, which also says that for every reaction, there's an equal and opposite reaction. It means that the Earth is being pulled towards this mass as well. But it's just heavy enough, it's not accelerating much. All right, so this is called the universal law of gravitation. It tells you that this G is experimentally found, by the way, using, not in Newton's time, but quite a bit later, using two lead masses on a pendulum, on a special pendulum. This G turns out to be 6.67 times 10 to the minus 11 newtons meters squared kilograms squared. And that's called the universal gravitational constant. Okay. Now, let's see if we can do this real quick. clearly, and this is the force of attraction between any two masses. Not just the mass of the Earth and the mass of this thing. If I put M1, M2 here, that'd be the force of attraction between mass 1 and mass 2. Now, this universal law of gravitation has to be responsible for the force on the center on the surface of the Earth being mg. Now, on the surface of the Earth, the distance between the center of the Earth and that object, that's the radius of the Earth. I'm going to call that r sub e, radius of Earth. So, mg has to be that universal law, mass of Earth, mass of the object, and in our case, the distance would be radius of Earth squared. So, the little mass that's on the Earth, that mass cancels out of this expression. I know G is universal gravitational constant, mass of Earth over radius of Earth, over the square of the radius of the Earth. I could actually get the mass of the Earth if I knew the radius of the Earth, couldn't I? And you get radius of the Earth by noticing how far away when you're on the ocean where the horizon is. Once you know G and that stuff, you can figure out exactly what the mass of the Earth is, and people did that. And that's one way you check. I mean, that's one way you can see that stuff. Okay. I guess I don't really have any further time. Why don't you go ahead and check for next time, in addition to your homework problems. I mean, this isn't going to be graded. This is just for your own fun. Why don't you go ahead and look up what the radius of the Earth is? Look up that V, and just go ahead and figure out what the mass of the Earth is. Oh, yeah.
That